Hey everyone, Professor Soroy here, and welcome to our very first organic chemistry chapter. This is structure and bonding. Most of this should be a review. We'll introduce a couple new terms that we'll carry on, but we're mostly going back and reviewing some hybridization and some Lewis dot structures and just making sure everybody's on the same page because a lot of this course is structures and bonding. It's all drawing pictures. There's very little actual math that we're going to be doing, which is one of the reasons I went into organic chemistry. But we'll talk more about that later. So before we dive too far into it, let's just outline kind of my advice I give to almost all my courses. I have this one tailored a little bit more specifically to you. But please remember to ask questions early and often. I'm available to work with you in person, online, using Zoom. We can communicate via email. You can send me pictures of your work. I'm more than willing to help you. This is my job. It's what I love doing. So please reach out early and often is the goal. That way, when you actually are stuck later in the semester, you're not going to hesitate to email me, right? So review the syllabus. I put a lot of time into making the syllabus. I understand that you're not going to sit down and read my 10-page syllabus or whatever it is. But the more familiar you are with the kind of the key points and my expectations, the better you'll navigate through the course. So I did put a lot of time into that. And most of the time, if you have a course-related question, it's in there somewhere. Please ask me, though. I'm not going to just send you to the syllabus. I'm not going to say, hey, it's on page 5, find it yourself. I will show you what I'm talking about, but most of the guidelines are in there, so you know what to expect from me and what I expect from you. So this is a continuation of General Chem 1 and 2. A lot of the stuff you learn in Gen 1 and Gen Chem 2 are not being applied, but we'll review the stuff that is, like we're doing in this chapter right now. And I will continue to point out throughout the semester if something is a review or if it's new. And if you ever feel like that I'm going too fast or it's a concept that I'm breezing over that it seems like I expect you to know, again, please ask questions early and often because I'm sure you're not alone. And sometimes I forget what you learned or how depth we went into it, or maybe you have a different background. So I will stop the presses and work on whatever the concept you need to catch you up. And again, that's what we're kind of doing in this chapter. So chemistry is cumulative. I'm sure you all know that if you're in organic by now. But this course is just more so. It's literally everything we do, the first couple of chapters of review, but we start building up this foundation of organic chemistry, which is just crucial to understanding anything else that occurs. So I always use the analogy that chemistry is like a language, and you really need to give it the time and energy that learning a new language requires. So organic in particular is a lot different than some of the stuff you've seen previously. So just start slow, get the basics down. And I'm not saying that it's basic like it's simple. The basics are foundationally challenging material, but you really need to get these down before we move on. And I'd rather slow the course down and make sure you understand the material instead of just rushing through it and saying, hey, we covered all 10 chapters or whatever it is. I want you to cover the chapter until you get it right. So communicate with me so I know what's going on. Yeah, chemistry is demanding. Again, I'm sure you've all realized this between this course and your other courses, but it requires a lot of independent work, especially the way I have the course designed. So make sure you're scheduling this into your week, right? So spend 2 to 3 hours outside of class per credit per week, right? This is a 4-credit course. That's putting you at 8 to 12 hours a week on this one class. Now, some of you might need more than that. Some of you might need less. I'm just telling you to schedule that in now because I've seen it time and time again where at the beginning of the semester, like look at this one lecture slide. It's maybe lecture show. It's probably like 30 slides. It's all review. You're like, oh, chemistry's not too bad. You pick up another class or another job. And next thing you know, 4 weeks down the line, you don't have the 10 hours a week you need to start doing aldehydes and ketones or whatever it is. The course gets challenging quickly. So block it off now, and that way if you don't need the time, you can use it for another course, another activity. But if you don't block it off now, you won't have it when you actually need it. That's just my advice. Do whatever you want. I'm telling you how I learned, not necessarily how you learn. And my goal is to figure out how you learn as well. And just kind of to sandwich it off, right? Ask questions early and often. So I really do mean that. Please, please, please. I love organic chemistry. It's my favorite course. So let me talk about it. Okay, here's the outline for the chapter. You should recognize a lot of these in review, right? The nucleus you've seen probably at the beginning of Gen Chem 1. Orbitals we'll talk a little bit about. Electron configurations are helpful. And then we'll get into a little bit of chemical bonding theory, just showing kind of like why these bonds are occurring. valence bond theory you might be familiar with. That's kind of where we get our structures, our tetrahedrons, and our trigonal pyramidals, trigonal planar type things. These are all hybridizations. Remember your sp3, sp2, sp1, stuff like that. They come up throughout the chapter and within the organic course, and a lot of people find them very helpful for visualizing these three-dimensional objects. We'll go into some specific hybridization of nitrogen, oxygen, phosphorus, and sulfur. And really, like, the crux of this entire chapter is this one bullet point, and it's only a few slides at the end. But this is what I mean by the cumulative nature. We use all of these slides to really start doing this again. So this should be mostly review. And this should be review too, but we're going to start applying it to maybe some chemicals and some molecules you've not seen before. Okay, so this is organic chemistry. These are what these structures look like. I'm not going to have you draw or name or do anything like that, but I want you to see the level that chemistry can get to. Not to scare you, but maybe to excite you a little bit and to show you like how complicated this can get. And definitely by the end of this semester, next semester, you'll be able to look at this a little bit more comfortably. Right, OxyContin, we can talk about that, cholesterol, and penicillin, right, or a penicillin derivative. Right, but you should be able to look at some of this and recognize some things, and the rest you might be super overwhelmed by, and that's completely fine. You've not seen most of these structures before, maybe in movies and stuff, but this is where we're heading to an extent. But let's start back at something you are familiar with. Right, so here's your periodic table. Our entire course really is just these highlighted elements, right? Hydrogen, carbon, I mean, the definition of organic chemistry is carbon containing. So we're going to be talking lots about carbon, lots about hydrogens. And then we just kind of fill in the blank with some of these other ones. These halogens pop up here and there, and then these four little guys. But honestly, it's mostly carbons, hydrogens, and oxygens, and then the halogens in there. And that sounds silly, but it's 2 semesters worth of material for these, I don't know, 10 elements, whatever it is. Yeah, I got it right, 10, cool. Okay, and we all know, hopefully, that you have your nucleus in the center with your neutrons and your protons, and then your electron cloud that takes up most of the space. This is a better space-filling model, if you can kind of see that. And I think this is just introducing you to a review of what the nucleus looks like and where the electrons can be found. Most of the, or let me try this again, all of the chemistry we talk about is the electrons. This is what does all the work. The electrons are bonding with each other to make covalent bonds or ionic bonds, and that's how we form molecules. It's this change of electrons. So understanding how the electrons are organized, and at least what you're working with, will allow you to have a better understanding of what's going on. I remember when I was at undergrad studying organic, losing my mind. My friend that was a bit older than me, who'd already passed, he was like, "It's all electrons, man. It's all electrons." I was like, "You're crazy. There's so much going on in here." But really, if you can figure out where the 1 electron is or the 2 electrons are and where they want to go, that's the answer, like every time, with very few exceptions. So it's a game of electrons. So the electrons are held in these orbitals. Remember these S, P, D, and they didn't show the F orbital because I think it's a monster to draw. Everybody likes the S orbital. It's nice and circular. Like, okay, this isn't too bad. Here's your dumbbell-shaped P, your clover-shaped D orbitals. That's how I draw them. That's as good as I'm going to draw them. I'm not going to be having you draw these very often, but this should be a review about the major orbitals we will encounter within the organic molecules. And then here's your energy level. Remember, we can fill in those orbitals: 1s2, 2s2, 1s2, 2s2, like 2p6, your electron configurations, they're called. I don't have my periodic table on me right now, otherwise I'd tell you when this is. Something that ends in D10. I go back and figure it out. It's not on there. Oh, might be zinc. 3D10 should be right about there. Am I going to be having you do electron configurations again, like from Gen Chem 1? No. I just want you to recognize that these are the electrons we will be working with when we're doing chemical reactions. And then the p orbitals can be represented into 3 different dimensions: the x axes, the y axes, and the z axes, about how they are oriented. The z coming out of the board, the y going up and down, and the x going across the plane there. I will say a lot of what we do is 3-dimensional things represented in 2-dimensional space. So that is the challenge. You will hear me say that phrase a lot. Oh, we're doing three-dimensional things in a two-dimensional space. So if you're having trouble seeing something two-dimensionally, we might have to look at it a different way, but let me know. Like I see the Z orbital coming out of the board at me. Okay, remember our shapes, our favorite tetrahedron. This is like what carbon wants to do. Carbon loves making 4 bonds. And he's a tetrahedral sp3 hybridized center. This is giving you some memories a little bit. 109.5 degree bond angle. That shows up somewhere else. Forget my, not Celsius. I always write Celsius after degree by instinct. And then, so this representation here is super important. So the bonds in the page are in the plane. Like, so they're flat. That'd be like a flat right angle, I guess. And then the bonds with the dashed, I'm not going to draw over the molecule, but the bonds with the little dashes, that goes back into the board or into the computer or into your paper, whatever it is. And the wedge comes out of the board towards you. So you'll always have 2 in the plane. I should have made a wedge. 2 in the plane, 1 going back in, and 1 popping out. This is the notation we use. Again, here, I promised you I'd say it over and over again, to represent three-dimensional things in a two-dimensional space. And this gets some getting used to. Here's again a kind of a ball and stick model with some shadows on there. And we can make models in class. That's what they're doing down here. Again, see the wedges. They're really trying to show you that this is a three-dimensional thing. So I think they're doing an okay job with these graphics. I guess it's called the Van 't Hoff model. I didn't know that, so don't worry about that. But we'll do this with a few other things. And the orientation of the molecule in space is super important, and more particularly of the atoms in that molecule. We'll get there in a few chapters. Okay, so these line bond structures or Lewis dot structures, this should be a partial review. Maybe you never drew methanol, but you should be able to look at these molecular formulas and draw your Lewis dot structures. If you want to practice that right now, you can pause the video, have them on the next slide as well. But I'm going to go through this pretty quick because this should be a review, but remember, let's do methane first. If you didn't have me for Gen Chem, I think 1 is when we learned this. We did a little bit in Gen Chem 2. I always take the central atom, which in most cases is the first one, or it's the it's the least electronegative, I think is the other trend. But the more you get familiar with this, the better. Like I know carbon always makes 4 bonds. 1, 2, 3, 4. And hydrogen always makes 1 bond. So like you just put them in there. And you got your molecule. Make sure you have all your electrons. I should have 8. I have 8, so I'm good. Nitrogen is my central molecule. Nitrogen loves to make 3 bonds and have a little lone pair on the top. It doesn't have to be on the top. This is how we generally do it. Like this is what nitrogen wants to do most of the time. So knowing that, just fill in the blank with hydrogens. It's where a little bit of experience comes into play. There is the long way of going through these. These are my hydrogens. And I will let you review that on your own. But if you are having trouble drawing these to start, this is a great place to review Lewis dot structures. Water, you get that sweet vent shape with the lone pairs. Put the hydrogens in. Count your electrons. All right, now methanol. This is our first organic compound. This is where it gets tricky because, not tricky, but I mean, practice makes perfect, right? But the way this is written, they're telling you the order of the molecule. You have a CH3 and then an OH. But hydrogen always makes 1 bond, so these hydrogens aren't actually attached to anything except the carbon. So I'm going to draw it down here, right up there. Carbon with 3 hydrogens on it. Attached to an oxygen and then a hydrogen. That's what that other half is. And you should put the lone pairs in for now on the oxygen to be good students and good bookkeeping. Eventually we'll leave those off. We'll get lazy organic chemists. So that's what methanol looks like structurally, and then this is a way of representing it. So again, be careful because I wrote CH3. Man, this pen's not doing great today. CH3OH. These hydrogens are not like in the line of the bond, so maybe I'm confusing you more. But you'll see what I'm talking about when we get some larger molecules. Let's see, electron dot structures. So for the most part, I expect you to get to these line bond structures pretty quickly. You do not want to be drawing out all the electrons for these organic molecules. They're very large. If this is what you need to do to start, for sure, start where you're at, but get pretty comfortable drawing the lines out. It makes life a lot easier. And then we get to something that's called just the line structure or a skeletal structure, which makes things way faster to draw, but it can be a bit challenging for students to get there. Okay, so I mentioned this a little bit earlier. Like hydrogen loves to make one bond. Carbon loves to make four. Nitrogen makes three and has a little lone pair. Oxygen will make two bonds. It'll look either like that, or sometimes it'll have a double bond. Double bond to oxygen down to, I don't know, a carbon. It has two lone pairs on still. I'll put the carbon with some hydrogens on it because carbon always makes four bonds. Right, so oxygen can do that as well. And then your halogens generally always make one bond and are kind of stuck off on the side of things. So being familiar with these trends makes life easy. Most of what you're doing is carbon, oxygen, and hydrogen. I promise you. And they throw these on the side. Okay, this doesn't show up till chapter 3 in your book, and I think it's a great disservice to not introduce the alkanes like immediately on day 1 of the class, because you need to just memorize how to draw these. You need to know that methane is 1 carbon, that butane is a 4 carbon chain, that heptane is a 7 carbon chain. The sooner you have those flashcards down, or however you need to memorize this, the better. So I'm telling you on day 1, and then it shows up again in chapter 3, and then we just completely build on this. I think for me personally, it was like pentane and onward made sense because those are like Latin prefixes I was familiar with, and I was always getting methane, ethane, propane, and butane kind of mixed up. I don't have a perfect little rhyme for you at all, but that's the game I played. I got these last 6 down, and then the first 4 I kind of struggled with, so I just did them so many times that it was no longer a problem. And that's a lot of how it works. Just repetition. I know you've heard this all before, but getting these down. And the reason you need to know all of these is because these are the bases or the root names for every other organic compound. For example, methane is 1 carbon. It's got 4 hydrogens on it for sure, but if I replace one of those hydrogens with an OH group, so I have CH3OH, we just saw this on a previous slide, right? Now it's meth and all. It's an alcohol that ends in OL. You can do that for all the rest of these 9s, like ethanol would be CH3CH2OH. That's ethanol. So it's a bit beyond the chapter 1 stuff, but again, I need you to realize how important it is that I could remove one of those hydrogens and replaced it with an OH group. I added a new functional group to these root molecules, and I've changed the identity of the molecule. So you memorize 10 base names and a little functional group, and now you know 10 alcohols. You memorize 10 more functional groups, now you know 100 compounds. So I'm memorizing 10 things, 11 things, right? So it's a lot at first, but that's what I'm giving to you on day 1. Brush your teeth, practice your alkanes, you know what I mean? Just like I had you all memorize your strong acids back in Gen Chem 2. This is your mantra for the semester, these first couple weeks. All right, so I mentioned functional groups briefly. This, again, is kind of like the next 2 semesters worth of functional groups, so don't get super overwhelmed at once. I think we hit alcohols like towards the very end of this, organic 1. They have the aldehydes on there. Yeah, or halides, not yet. So there's other ones that show up, but like these pop up here and there throughout the semester, so another list of things to start getting down sooner than later. You'll notice on the syllabus, like we hit alkenes in a few weeks, and followed by alkynes, right? We get pretty cumulative alcohols at the end. That might even pop up in next semester. I gotta look at my syllabus. I don't have it with me. My point is that this R group right here represents all of those alkanes I had before on the previous slide. R just stands for like any carbon chain. Here are some examples. So being able to identify a compound as an aldehyde or a ketone quickly will save you time and allow you, not just time, but like allows you to actually understand what's going on. I think I drew, like back here, I drew this compound. It's a carbon with a double bond oxygen and 2 hydrogens on the side. That is an aldehyde. It's a carbon with a double bond oxygen, hydrogen on one side, and the R group can be a hydrogen or an oxygen, or sorry, a hydrogen or a carbon. R groups can be a bit tricky. They're like placeholders. They're not important for the most part. Here's an example of ethanal. Aldehyde, notice how all the endings, like ketones, end in, well, that's the best example, ketone. Carboxylic acids end in ic acid. What else? Alcohols, OL, end in OL, right? So there's a method to the madness here. I understand that when someone tells you to just memorize stuff, you kind of cringe. Trust me. I'm not sure how it's for you to know these things, though. Practice and start writing them down. Okay. Let's see. Lone pairs of electrons on ammonia. We usually include the lone pairs. You don't have to in this course very much unless they're doing something important, which means if they're in your reaction. So this is ammonia. This is a perfectly fine way to write ammonia now. We are all chemists. You're fresh organic chemists. Like, we know there's a lone pair there. We don't need to waste our time drawing that over and over again. If there wasn't a lone pair there, we'd draw like a negative charge to represent that. I don't think that exists, but that's how it works. Okay, here's your valence bond theory review. The whole idea of bonding is that if molecules are too close, these are two hydrogens, we want to push them together. If they're too close, the energy is wicked high because of those nuclei repelling each other. If they're too far away, they're not going to do anything. They got to see each other, right? Not going to bond if they're too far away. And if they're in that sweet spot where they're just the right distance, they'll share their electrons. Remember this whole diagram, right? They share their electrons and everybody's super happy. That's what's going on right here. Up electron, down electron. Notice the minimal energy on the left here. This is your energy. And, excuse me, they're giving you the bond lengths. Don't go memorizing bond lengths just yet. Don't go memorize energies just yet. But it's just showing you that, oh, you know what is important here, though? Should have just crossed that out. We release energy when a bond forms, and we have to put energy in to make a bond. That comes in handy a bit later. So if you're splitting a bond, you are putting energy in. You have to put in the right amount of energy with the right frequency to break that bond. So energy is absorbed when they break, and therefore when things bond together, they release energy. Okay, back to hybridization a little bit. This, again, is a review of what we talked about earlier. I introduced all of your s orbitals and your p orbitals. So you have 3 different p orbitals and 1 s orbital. These will combine to hybridize. I remember not getting this at all as a student. The whole idea is that this doesn't always happen, but for all intents and purposes, all of our central molecules will hybridize. This is what happens within the molecules we will be looking at in this course. I'm going to back a slide. Like, these are not hybrids at all. It's just an s orbital and an s orbital. They did not need to hybridize to bond. Whereas in order to minimize energy, orbitals will hybridize to form these hybrid orbitals. In this case, they formed 4 tetrahedral sp3 orbitals. I'm not sure why it's left. Oh, talk about that later. But yeah, 4 tetrahedral orbitals. And this is kind of what you picture, like your carbon center. Picture your carbon with your hydrogen and your hydrogen and your hydrogen. Back to that methane molecule. And the bond's coming out. Like, this is why this happens. My little 4-leaf over there. Oh, this is showing a single sp3 orbital, and this is showing them all overlapped. It's a little confusing for a diagram. So you get 4 of these. But generally, we represent them like that. This is why we end up with tetrahedral shapes. Methane, once again, CH4, methane, right? The first molecule to haunt your dreams. The bond angle is pretty important. Bond length, I don't have any specific questions right now that I'm going to ask you about bond length. We will look at trends later on, so I'm not saying, like, don't understand what a bond length is, but you don't need to memorize them right now. Okay, now we're building up a bit more molecules. If we take 2 of those carbon elements, carbon atoms, and remember, they love making 4 bonds. They're basically all showing up with these sp3 hybridized orbitals, and they got 4 of them total. Here's just that same overlap we want to do. We still want to make that bond. That's what's going over here. But they're going to call this an sp3, sp3. I think it should be a sigma bond, not an s bond. It should be sigma. usually represented like that, a sigma bond. Now we've made ethane, which is a 2-carbon chain. The bond angle is a bit greater here. Let me think about that for a second. We'll talk about it more in detail in a later chapter. But basically, this hydrogen is kind of pushing against that one. They don't actually not going to bond. They're going to push against each other and repel, kind of opening this one up. And it's also increasing the bond length, right, by quite a bit. This was 109. Now we have 153. But this is your 2-carbon chain, carbon, carbon. Your little white spokes are hydrogens, etc. So this is your ethane molecule, pretty commonly represented. I'll take a pause right here and just add that, like, we can represent this molecule in a bunch of different directions. Like, I can draw it carbon, carbon, and then put the hydrogens in. Putting them in no particular order. Like, this is still ethane. I just kind of rotated it. So 2 carbons, 6 hydrogens. So taking the time to look at a molecule from a couple different angles will help you see what's going on. It gets a bit more complicated when we start introducing double bonds, right? But we still get that overlap. These hybridize a bit different. They're sp2 hybridized. And then you get your pi bond overlap right up here. These are not the symbols I like. I'm just seeing these in depth now. Pi we usually represent as like a pi bond. And the S bonds should be sigma bonds. That's how I write it. That's how they're saying right there. You can call it a P bond if you want, but it gets a little confused with the P orbital, I would say. That's fine. Here's ethylene or ethene down here. It's got a carbon-carbon double bond, sp2 hybridized orbitals. And you should just know that. You remember that this has your electron groups. Let's see. You have a carbon double bond, carbon, hydrogens in. So you ask yourself how many electron groups are around that carbon. So there's 3 electron groups. Therefore, it is sp2 hybridized, trigonal planar, 120-degree bond angle. This is all a review from Gen Chem. I mostly care that you know the structure and the hybridization. sp3 hybridized tetrahedral, sp2 hybridized trigonal planar, stuff like that. Here they're showing you the ethene again, kind of the top and the bottom. A bit confusing, but you take your time to look at that. I don't want to talk too much about it, but they're kind of rotating some stuff around. Let me see different angles of your sp2 hybridized orbitals. With the unbound, this is a non-hybridized p orbital. And that's how we get our ethine or acetylene. Ethine is a triple bond. Again, these functional groups. Let me go back to the alkenes real quick. Ethene is an alkene. That's a functional group. Ethine is an alkyne. That's a functional group. The common name is acetylene. If you use like an acetylene torch, this is what you're burning. I mostly care of you being able to draw this structure, identifying that each of these are sp hybridized orbitals. They are making an sp. There's a sigma bond now. Okay. That's the free textbook at work. But so here's your sigma bond and your 2 different pi bonds. I'm not having you draw these weird funky orbitals. I'm telling you what you need to know. Be able to recognize how many pi bonds are in here, what the general bond angle is. Like, this is a linear molecule. It's 180 degrees. It's a straight line, like a stick floating around. That's going to change how it behaves in reactions and things like that. They're showing you the sp orbital again and all the other unhybridized p orbitals, just for more detail. Okay, so we drew ammonia earlier. Your favorite weak base, right? That's ammonia. As soon as you take any of those hydrogens and replace it with a carbon, it's now something called an amine. And now we're in the realm of organic chemistry. So, but this behaves almost identical to ammonia. If this is a weak base, this is also a weak base. Let's not sweat the bond angles too much, but this is called methylamine. It's actually the primary ingredient in making methamphetamine. I ordered this once when I was a grad student, not knowing what it was for, and I had to sign a bunch of paperwork, and I had no idea why. I realized they thought I was making meth, but I was not. I was just trying to do some simple experiments. Highly regulated compound. Methanol, we talked about a bit earlier. They're showing you these are the unhybridized orbitals because they didn't need to hybridize. This one has the hybridized orbitals. You wouldn't. The more you do this, you'll know. You're like, well, how do you know? How do you know? You can, for now, assume everything that is our central atom or our organic stuff is going to hybridize. Those are all sp3 hybridized orbitals. Your carbon, hydrogen, hydrogen, hydrogen. This is your carbon-oxygen bond. Your oxygen-hydrogen bond. This thing can rotate around. Again, I think students get hung up with like memorizing orientations. Like this thing is all vibrating and stretching and rotating and just bouncing around all over the place. It's like a snapshot of what this molecule looks like. I think I have some videos I can share that just show you a bunch of molecules bouncing around like and moving. That's what you need to be able to visualize. Yeah, like I said, it's kind of like a picture of a molecule in motion. All right, and for now, don't sweat all the. I know we talked about hybrid for a while, but like this is called a thiol if it contains sulfur, and then a disulfide if it contains, let me try this again. If it's just a sulfur on the end of a carbon, it's a thiol. If it's a sulfur sandwich between two carbons, it is a sulfide. We don't see this for a little bit in the semester, but what we did in this chapter so far is review hybrid orbitals, something you should be familiar with, and introduced some new organic compounds that you're not familiar with, right? So you should feel like, okay, I get some of that, and then go back and do the practice problems, and you'll get a bit more. Ask questions in class. Okay, now this is what we're going to be doing for most of the semester. This is called 2-methylbutane, and we'll practice naming this again in chapter 3. But these are all the same exact structure. We have 1, 2, 3 different ways of representing the same exact thing. It actually gets a bit more complicated. I'm not sure if I have next slides I'll draw right now. You can also represent it like this using just straight up lines. That's the same compound. I can do it like this. That's the same compound. So if you're a little confused, you should be. We'll talk about the line structure. I think it's on the next slide, but I want to make sure I'm emphasizing the point that these are 3-dimensional things moving around. Here's your butane backbone. Butane means 4 carbons, and then it has a methyl group on top, a 1-carbon methyl group. So I promise you we practice naming this over and over again. It's in chapter 3. But we're showing you what these structures can look like so you're not super overwhelmed by them. I'm a pretty big fan of the line structures down here. This one's pretty good too. This one's fine, but it gets really messy. This one's pretty good too. You have to recognize that this hydrogen, again, is not bound to that carbon. It's the other way around. So all the carbons are bound in this long chain. Okay, so the way line structures work, and this work example is just throwing you right into it. Every point where the line is or meets is a carbon. So I can go through. So they want you to tell you how many hydrogens are bonded to each carbon and get it like the formula. So it's basically just telling me what am I looking at. So every point on this structure that is an intersection or a terminal line is a carbon. So I have 1 carbon here and then 1 carbon there. That carbon is double bonded to another carbon. This carbon right is a carbon with 3 bonds. Carbon, carbon, carbon. Every point is a carbon, unless it's specifically something else like this oxygen. Okay? And the way these line structures work is the hydrogens are left out, because if I was to draw every hydrogen for my whole life, I'd still be drawing hydrogens based on the amount of molecules I've drawn. Right? But we know as chemists that carbon always makes 4 bonds. So go back to where I started. This carbon has 1, 2, 3 hydrogens off of it, because carbon always makes 4 bonds, right? Now I have 3 hydrogens and the 1 carbon-carbon bond. This carbon right here doesn't have any hydrogens on it because it's already got 1 bond, 2 bond, 3, 4, the double bond. I know it's a little messy with my drawing. There's no hydrogens on there. Hydrogen, hydrogen. That carbon has 2 bonds, 3, 4. That's the game. Fill in the blank with the hydrogens. This carbon has 3 bonds already. So how many hydrogens are going to fill in the blank? Just 1. Doesn't matter which way you draw it. This one has 2 hydrogens. Get a little messy. Draw H2. This one also has 2 hydrogens. H2. This guy has 1 hydrogen. This one has 0 because it has 1 bond. 2, 3, 4. Here's another CH3 up the side here, just like this one. I just represented it a bit more condensed. See how it can get messy? But that's it. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So C10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, H14, and 1 oxygen. Generally, this is how we represent it, like carbon, hydrogen, oxygen. We'll get more familiar with that. So this is carbone. They say what it's used for. Oh, it's in spearmint. That's right. See if I did that right. All right, cool. It's always good when I get it right the first try. A little cleaner of a molecule, right? They went and color-coded these. I'm not sure if you can see the 3 hydrogens are red, the 2 hydrogens are black, and the zeros are green, and the singles are blue. So we'll practice this. You should be able to look at any compound eventually. But this is a big molecule, right? Like, what we can go back and look at. Am I in my slides? No, I have it primed. Look at me. Almost like I know what I'm doing. So you can't draw a line structure for methane. That's just going to be CH3. Sorry, CH4. Ethane's not a very fun line structure to draw. It's literally just a line. But that would imply a carbon with 3 hydrogens and a carbon with 3 hydrogens. Propane's where it starts getting useful. I can draw 1, 2. Again, that's a CH3, CH3, and a CH2, all bound together. You'll notice I kind of flip the hydrogens out here. It could also be this like this. You can do CH3, CH2. These are the same thing. It's fine. These are both propane, a 3-carbon chain. Butane. Okay, or you can go the other way, just like down. I always count like peaks and valleys. I like when I'm transposing these. It's like I have 1 peak and then 1 valley, so I know like when I'm rewriting it if it's the right molecule or not. Here I still have 1 valley, 1 peak. It's the same molecule. You can also draw it the other way. You know, that's still butane. That's still propane. That's propane. That's propane. Right? I know this might be overwhelming. I assume it is. But the whole idea, I'm going to erase the stuff on the slide if I can. Making some room on this one slide. The whole idea is that when you have to draw something like octane, you don't want to draw out 18 hydrogens. You just count the peaks and valleys. You're just like 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. That's octane. I drew it in about 30 seconds. I can't do time very well. I drew it about like 5 seconds, right? Try drawing out all of that. It'll take you about a minute. I'm not saying you can't draw all these out. I'm saying it'll be much easier for you to move on knowing the line structure. It's going to take some time to get there. They introduced it in chapter 1. I feel like realistically you're not going to be getting it to like the middle of the semester, to the end of the semester. We won't be doing super giant molecules all the time either, so we're not going to be having to draw all of these out. But we do some naming, it gets confusing. And just when you're looking at stuff in the book, you know, they're going to represent it in all these ways. And I want you to know what you're looking at and be able to identify it. Here are the functional groups again. I think my intent was to show you how to draw all the functional groups out with some line structures. Again, you can think back to ethanol we did earlier, 1, 2, OH. The line structures only do carbons and hydrogens. You're not going to abbreviate anything else. That implies that there's a carbon here with CH2 and a carbon here with CH3. Right. I won't go too much in depth, but like here's your ketone. C double bond O. Ketone's right here. This is acetone. You know it as nail polish remover at home. It implies a CH3 here, a C with no hydrogens there, and a CH3 there. Right? It's just a faster way to draw it, and we haven't left the lone pairs out because we're getting lazy already as organic chemists. They're implied. We all know that they're supposed to be lone pairs in. And if you don't, well, the more you draw it, the more you figure it out. I'm not saying don't draw your lone pairs. It never hurts. Okay, so you'll notice that's the end of the chapter. As I promised, a bunch of review, and then we just did this, and that's all the line structure is drawing. The alkanes, the functional groups, that's the beginning of the rest of your organic life here. We skipped molecular orbital theory. If you're looking at the textbook, we don't need to go over that. If you love theory and you want to learn more about different types of bonding models, that's great. But for me, I don't think it's necessary to learn the material. And we will do that throughout the course. Make sure you're not just reading every single chapter, because we're not covering, first of all, we're not covering every chapter, and we're not covering every section in every chapter. I thought about skipping some of the hybridization stuff, but it does show up later a lot, and I want you to see it. So this is the way the course is going to be designed. This is how the lectures will be delivered. You'll have your chapter assignments to work on, and in-class assignments is the plan for this semester, fall 2023. So I appreciate your time. Please email me with any questions, and I look forward to the next chapter.